Matrix chain multiplication. Matrix chain multiplication problem is a classic problem in dynamic programming. Let us understand what is this problem and how can we solve this problem. First of all, the problem of matrix chain multiplication is of finding the optimal way to parenthesize a sequence of matrices. If you have matrices A, B, and C, what is the optimal way of parenthesizing them such that when you do multiplication of these matrices, the total number of scalar multiplications should be minimized. This is the aim. What did I mean by this? Let us dive a bit more deeper and understand the concept with clarity. If you have matrices A1, A2, A3, A4 and you want to perform multiplication, there can be different orders in which you can multiply these matrices, and depending on the order of parenthesization, the total number of scalar multiplications will differ. One way is you can first multiply A1 into A2, then with that result you can multiply A3, and then with that result you can multiply A4. This is one way of parenthesizing. Another way is, let us say you want to do A2 into A3 first, then you will multiply A1 with the result of A2 and A3. After that, with this result, you will multiply A4. This is another way of parenthesizing. Keep in mind that when I say order, I only mean the order of parenthesization. You can't interchange the order of these matrices. That is, you can't do this like A3 into A2 into A4 into A1. You cannot perform this multiplication like this. This is wrong. Moreover, it may not even be possible to multiply in this manner. Why did I say that? Why did I say that it may not even be possible to perform this multiplication? The reason is, whenever you perform matrix multiplication, something like A1 into A2, if you want to do this, there is a condition to be satisfied. The condition is number of columns in A1 should be same as the number of rows in A2. Only under this condition, you can perform multiplication between any two matrices. If that is violated, it is not even possible to do a multiplication. For example, if A1 is having 3 rows and 4 columns, and let us say A2 is having 4 rows and 5 columns. In this case, the number of columns in A1 is same as the number of rows in A2, and because of this, it is possible to perform multiplication between A1 and A2. What if I am trying to do A2 into A1 with the same dimensions? Then A2 is having 4 rows and 5 columns, while A1 is having 3 rows and 4 columns. In this case, when you're trying to do A2 into A1, the number of columns in A2 does not match with the number of rows in A1. Because of this, A2 into A1 is not even possible. You can't perform this multiplication. This is why you have to keep the order of matrices, but it is possible to change the order of parenthesization. This is where you can change number of scalar multiplications. One more thing, when you multiply A1 with A2, what is the dimension of resultant matrix? Let us say A1 into A2 is C. Then what is the dimension of C? It is 3 by 5. How did I understand it is 3 by 5? The reason is, whenever you perform matrix multiplication, the resultant matrix will be having same number of rows as the first matrix and same number of columns as the second matrix. This is why I am able to say when you do A1 into A2, the resultant matrix, let us say C, will be of size 3 by 5. This is how I can determine dimension. Next question is, how can I identify the number of scalar multiplications that are required in multiplying A1 with A2? A1 and A2 are two matrices. I want to do multiplication. Then what is the total number of scalar multiplication? That is, when you multiply any two matrices, a lot of multiplications have to be done between different elements of the matrices. What is that total number? That is what I'm asking. In order to find out that, there is a shortcut. It will be 3 into 4 into 5. How did I find this out? 3 is the number of rows in the first matrix, 5 is the number of columns in the second matrix, and 4 is the number of columns in the first matrix, which is same as number of rows in the second matrix. Whenever you get two matrices which you want to multiply, you can directly find out the total number of scalar multiplications that are required in order to multiply these two matrices. So this is how you will understand total number of scalar multiplications. Next question is, how do you identify the right parenthesization so that in the complete operation of multiplying all these matrices, you can minimize the total number of scalar multiplication? For this, we'll use few notations. I want you to be familiar with the notations first. If these are the matrices A1, A2, A3, etc., then I'll put the notations here. A1, A2, A3, A4. These are the matrices that you are having. Let us say you have till AN. If this is the case, any matrix AI, any random matrix AI will be considered to be of dimension Pi minus 1 cross Pi. This is the notation we'll use while solving this problem, matrix chain multiplication. Why are we having notation for this? Because we should be able to identify dimension of each matrix so that we can multiply. And why is this dimension followed? Pi minus 1 cross Pi. This is because if you have a matrix before this, let us say Ai minus 1, this should be of dimension Pi minus 2 cross Pi minus 1 so that number of columns in this matrix is same as number of rows in this matrix. Because these should be the same value, I am using Pi minus 1 cross Pi. Okay. So how can you write the dimension of these ones? A1 will be P0 by P1. A2 will be P1 by P2. A3 will be P2 by P3 and so on. What will be AN? It will be Pn minus 1 cross Pn. So this is how the dimension of these matrices can be defined. Next thing is, we have to determine the optimal order to multiply these matrices with minimum number of scalar multiplications. You are clear with the rules now. So the next thing is, we can step into finding this out. One more thing I want to do is, I want you to be very clear in this point that when I change the order of multiplications, there can be very huge number of differences in total count of scalar multiplications. In order to prove that, I'll just take two examples and I'll show you how much of a difference will it make when you alter the order of parenthesization. I'll take four matrices just for example, A1, A2, A3 and A4. So I'll have A1, A2, A3 and A4, and I'm just defining few dimensions for these. A1 is 5 by 15, A2 is 15 by 3, A3 is 3 by 10. See this, whenever I am defining these dimensions, I am making sure that the number of rows is same as number of columns of previous matrix. Only under this condition, multiplication can be done. What about A4? It has to be 10 by something, let us say 4. If this is the case, let us just try out two different parenthesizations and we'll see what is the difference in output. That is total number of scalar multiplications. How are they differing when I'm changing order of parenthesization? First parenthesization can be, I have these matrices A1, A2, A3 and A4. Let us say I want to parenthesize like this. I want to make A1 and A2 together. Then I'll multiply A3 and A4 and then I'll multiply these results. This is how I want to perform this particular multiplication. What will happen in this case? In this case, A1 into A2, when I do this, what will be total number of scalar multiplications? For this one, it will be 5 into 15 into 3. How did I understand this? Because 5 is the number of rows in A1, 15 is the number of columns in A1, which is same as number of rows in A2, and 3 is the number of columns of A2. This is how I understood. A1 into A2 will take 5 into 15 into 3 scalar multiplications. Plus, what are the other scalar multiplications to be done? I have to do A3 into A4. When I do A3 into A4, what happens? It will be 3 into 10 into 4. This will be the total number of scalar multiplication in doing A3 into A4. Next step is, after I do both these, I have to multiply these results. When I multiply these results, how do I understand scalar multiplications? For that, I first have to know what is the dimension of A1 into A2. A1 into A2 will have same number of rows as A1, that is 5, and same number of columns as A2. So 5 by 3 is the dimension of first result. Second result dimension will be 3 by 4. That is 3 is from here, 4 is from here. If this is the case, then when I multiply these two results, what will be the total number of scalar multiplications required there? It will be 5 into 3 into 4. So this will be 5 into 3 into 4. What is the total here? 5 into 15 is 7, into 3 is 225, plus 3 into 10 is 30, into 4 is 120, plus what is the final one? 5 into 3 is 15, into 4 is 60. So when I do this, 225 plus 120 plus 60. So 120 plus 60 will be 180, plus 225 will be 405. So total number of scalar multiplication is 405 if I am using this order of parenthesization. That is, I'll do A1 into A2 first, then A2 into A4, A3 into A4, and finally I'll multiply those results. Let us just try out one more parenthesization so that you will be clear how much is the difference coming up in total count of scalar multiplications. Instead of this, if I do it like this, if I have A1, A2, A3, A4, the same matrices, instead of the previous parenthesization, I'll do A2 into A3 first, and then I'll do A1 into this result, and then I'll do finally into A4. If this is the order that I want to do, then what will be the case? First thing is, I want to do A2 into A3. When I do A2 into A3, what happens? In this case, A2 is 15 by 3, A3 is 3 by 10. So total number of scalar multiplications will be 15 into 3 into 10, which is 15 into 3 is 45, into 10 is 450. So here you can say just this single operation made 450 scalar multiplications. In the previous case, complete multiplication was giving you 405 scalar multiplications. So this is the margin of difference. Let us just proceed with this so that you will see total margin. Next step is, now A2 into A3, what is the size? It will be 15 by 10. Where did I get this 15 by 10 from? From here. 15 is the number of rows in A2, 10 is the number of columns in A3. Next thing, I want to do A1 into A2 into A3. So A2 into A3 result you have, which is 15 by 10. A1 is 5 by 15. So what is the scalar multiplications required for this? If I want to do A1 into A2 into A3, for this A2 into A3, I already have the result. Scalar multiplications will be 5 into 15 into 10. What is the result of this? 5 into 15 is 75, into 10 is 750. For doing this multiplication, I want another 750 scalar multiplications. So what is the result? Here it will be 5 by 10. A1 into A2 into A3. This total matrix will be of dimension 5 by 10. Next step is, I want to do A1 into A2 into A3. This result I already have. This I will multiply with A4. This multiplication, A4 we know is of 10 by 4. So total number of scalar multiplications will be 5 into 10 into 4. What will this be? 5 into 10 is 50, 50 into 4 is 200. So total number of scalar multiplications 450 plus 750, which will be 1200, plus 200. So this total comes out to be 1400. If you compare with the previous parenthesization, total number of scalar multiplications was 405, but now it is 1400. So it is more than 3 times of the previous approach. So that much is your additional time, additional cost that is required in order to do this particular multiplication. So at this point, you should be clear that parenthesization has a very big effect in matrix chain multiplication. What is our aim in this particular problem, matrix chain multiplication problem? Our aim is to find out whichever is the best way of parenthesizing. If you have these 3 matrices, how should you parenthesize those so that you can do this with minimum possible number of scalar multiplications? Now let us go into the algorithm. What is the algorithm we should follow in order to find out the best possible way of parenthesizing in order to optimize the number of scalar multiplications? Let us get into this problem now. At this point, given that you are very clear with the concept, it will be more interesting to understand. That's what I want. I want you to be clear about the concept at every point. Let us get into the algorithm. How can you find the minimum possible number of scalar multiplications? The idea is to break this problem, which is a larger problem, into smaller sub-problems, and then we'll store those results so that further redundant calculations can be avoided. This is the idea we are going to follow. So this is the basic of dynamic programming. In all the dynamic programming problems, we'll have this pattern. That is, this certain criteria will always follow, that we'll break it into smaller problems. Problems will be such that they'll be repeating. What we'll do, we'll store the smaller results so that we don't have redundant computations. This is the basic of any dynamic programming problem. Let us see the algorithm that can be used. First thing, in order to find the best way of parenthesizing, first thing is we want a dynamic programming table. We know in dynamic programming, there should be some way of storing the result. So in order to store all the smaller results, we'll have a DP table. What will be the DP table? For this DP table, any particular value dpij, this will be a 2-dimensional table, a DP table. In this table, any particular element, any particular block dpij, what will this represent? Whenever you are defining a dynamic programming table, first thing you want to know is what is the significance of any particular block in this. What does the block represent? It represents the minimum number of scalar multiplications that are needed to compute the product of matrices from AI to AJ. This is important. Why is it AI to AJ? Keep in mind, it is not AI into AJ. It is the product of all matrices from AI till AJ. That is, if I am multiplying all these matrices from some point which is AI till some other point which is AJ, if I want to multiply all those matrices, what is the minimum number of scalar multiplications using which I can do this? This is what any single block in this matrix will represent. Okay. So at this point, you know what each entry in the DP table is representing. Next thing is we want to solve this using recursion. For any recursion, you need a base case. What is the base case here? Base case is when you have only one matrix. If you want to multiply a lot of matrices, there may be a lot of scalar multiplications that are involved. But your base case is when there is only one matrix. In one matrix case, what happens? It will be dp of II. Why is it II? Because there is only one matrix. So starting from that matrix and ending in that matrix. What will be the total number of scalar multiplications required? Think about this. If you have only one matrix, what will be the total number of scalar multiplications required? It will be 0. 0 because you have only one matrix, there is no multiplication to be performed. Whatever you have, that is the answer. So if it is one matrix, the total number of scalar multiplications will be 0, and that is your base case. Now that you have the base case with you, you should write recursive relation or recurrence relation. How can you write the recurrence relation for this problem? Recurrence relation, it should give you how to find out the answer for one particular block, any particular block dpij. How will you find out the answer? This is what recurrence relation will tell you. In order to write a recurrence relation, you have to break it into a smaller problem. How will you break it into a smaller problem? If you have this as your main problem, you can break it by saying, I want to parenthesize it at some point here. If I want to break it there, then there may be different ways of parenthesizing, and what can it be? This can be my way of approach. So I am saying I will try different points at which I can break this into two subparts. How can I break it into two subparts? If I have from ai till aj, let us say ai and something 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 till aj, these are the matrices I want to multiply. I will say that is some point k is there, which I'll call as split. So ak is the matrix at which I want to split. What am I saying? I will already have the result till ak. I'll already have the result from ak plus 1 till aj, and I want to find out if that is the case. If I already know both these results, then what is the total number of scalar multiplications required in multiplying this part with this part? If k is the point of split, then what is the minimum number of scalar multiplications required? This is what I want to find. This will be my one particular point of recurrence relation. How will I write the recurrence relation? If I want to write a recurrence relation, let us say I want to write for dpij. dpij. How will I fill any particular element in the matrix? For that, I should find minimum. That is, a lot of splits may be possible. I can split here, 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 and so on. Among all the splits, I want to see which is the best possible split, which gives the minimum value. So minimum of I less than or equal to k less than j. What is k? K is the split. So I can split here, 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 and so on. Whichever be the split that gives me the best result, I'll choose that as k. So minimum among these, what should I minimize? I should minimize scalar multiplications. So when I consider scalar multiplications, one is the minimum number of multiplications required to find out this answer, the answer on the left side. Another contributor is minimum number of multiplications required in order to find the right side answer, and then the minimum number of multiplications required in order to multiply these two results. This is the total number of scalar multiplications required. So how can I write the left part? It is already I would have computed dp of ik. So this is the beauty of dynamic programming. Here I am dividing it into smaller problems. So if I want to find the answer for any particular split k, I would already have found the answer for smaller parts and stored it in this dp array. So dpik plus, what about the right side? It will be dp of k plus 1 j plus, what will be the last factor? Last factor is the total number of scalar multiplications required in order to multiply the resultant matrices. One resultant matrices in the left side, one resultant matrix in the right side. I want to multiply these two matrices. Then we already know scalar multiplications required will be pi minus 1 into pk into pj. How did I know this? How did I know this is the total number? That is because the dimension of the resultant matrix from ai to ak, that will be Pi minus 1 cross Pk. This is already known because from the rule of matrix multiplication, we know this is what will be the dimension of this resultant matrix. What about the dimension of this resultant matrix from AK plus 1 to AJ? If I do that, it will be Pk. This is the dimension of that matrix, Pk cross Pj. If I want to multiply this matrix, which is Pi minus 1 cross Pk and Pk cross Pj, what will be the resultant dimension? Resultant dimension will be Pi minus 1 cross Pj, and total number of scalar multiplications will be Pi minus 1 into Pk into Pj. So this is how I found this out. So the next thing is, I know if I want to fill any particular block dpij, I can find it using this formula. I also know my base case is dpii is equal to 0. So what is the next step? Next step is, step number 4 is, you have to fill the dp table diagonally. This is the important part. You have to fill it diagonally. Why should you fill it diagonally? There is a reason why you are filling it diagonally. The reason is, your dp table will look something like this. This will be your dp table. So it will have 1, 2, 3, 4. These are the matrices. 1, 2, 3, 4. I will be filling the total number of scalar multiplications required for each thing. When I fill diagonally, the base cases will always be the diagonal element. That is, dpii, dp11 will be 0, dp22 will be 0, dp33 will be 0, dp44 will be 0. This is my base case. Then I have to fill this diagonal, this diagonal. Finally, where will my answer be? Answer will be in this particular block, dp14. How can I write this? In general terms, I can write it as, my final answer will be present in dp1n, where n is the total number of matrices to be multiplied. So if I follow this algorithm, then my final answer will be present in dp1n, where n is the total number of matrices. Let us just go through this algorithm once more, and in the next lecture, we'll have a complete illustration, a pure demo by taking few matrices and understanding how each of these blocks are filled. And then we'll also go through the pseudocode that can be used to write this algorithm. So here, if you are going through the algorithm once more, first step is to understand what is each element dpij in this dynamic programming table. Next step is to understand the base case. The base case is the case which says that if you have only one matrix, then the total number of scalar multiplications required is 0. This is the base case. Once you understood the base case, the core of this algorithm, the heart of this algorithm is in identifying the recurrence relation. Once you identify the recurrence relation, you write it correctly, you are done. After this point, the whole dynamic programming boils down to this. Whenever you are writing a dynamic programming algorithm, once you write the recurrence relation correctly, your whole algorithm is done. So here, what is the recurrence relation? I want to find the best split k, which will give the minimum value. That is what I'm trying to find. For the best split k, what happens? There will be one part which is having all the matrices from ai to ak, and the other part which is having matrices from ak plus 1 to aj. When I do this multiplication, what is the total number of scalar multiplications required? That is same as the total number of scalar multiplications required for multiplying first k matrices, sorry, not generally first k, ai to ak, then the second set of matrices, that is ak plus 1 to aj, whatever be the minimum scalar multiplications required for that, and then finally I have to add the total number of scalar multiplications required to multiply these two resultant matrices, that is this particular resultant matrix into this particular resultant matrix, that is pi minus 1 into pk into pj. That is what we had explained before. Once you are done with this, you have the recurrence relation. Then you have to fill the dynamic programming table, this table, starting from the diagonals. Then you have to progress to the next diagonal, and so on till you reach the top right corner. So whichever be the final value present in top right corner, that will be your final result on the total number of scalar multiplications to be performed. One more thing, what is the time and space complexity of this algorithm? Analyze that, it is better that we first write the pseudocode and then understand, because if you follow this algorithm from here, it will be difficult for you to comprehend. When we write the pseudocode, it will be very clear where the loops are and what is the total time complexity. So we'll discuss it there. For now, just understand that this is the algorithm. In the next lecture, we'll do a complete demo. We'll take few matrices, we'll have few dimensions, and then we'll fill the complete DP table one by one, so that you understand how the filling is happening and what exactly is the procedure. After that, we'll go through the complete pseudocode, understand time and space complexities. Okay.